This video will look at some of the properties of shapes and lines. Okay, so to begin with, let's start with some of the simplest, and that's the angle sum of a triangle. ABC here, angle A, B and C, adding up to 180 degrees. Now this is only true in the geometry of Euclidean spaces. That's the geometry of flat spaces. In other geometries, the angle sum of a triangle can be greater than or less than, depending on whether the geometry is positively curved, in which case it's greater than, or negatively curved, in which case it is less than. But in flat space, the angle sum of a triangle adds up to 180 degrees. All right, next bit. Let's have a look at the angle sum of polygons. So the sum of the exterior angles of convex polygon, that means no interior angle greater than 180 degrees, is 360 degrees. So all these exterior angles of polygons, convex polygons, adds up to 360. So A, B, C, the exterior angles of the triangle, of the quadrilateral, here the pentagon, and so on, all add up to 360 degrees. You can keep going the same way here. Hexagons, nonagons, all the rest of it. Okay, let's have a look at parallel lines and transversals. So we have parallel lines here. Now in Euclidean geometry, parallel lines stay the same distance apart forever. They never converge or diverge. Again, in positively or negatively curved geometries, that's not the case. Now the following angles are equal, so you can see that A and C, because they're vertically opposite, just as D and B are equal. E and G are equal because they're vertically opposite, and the same H and F. Corresponding angles, so C and G here are corresponding, B and F are corresponding, A and E are corresponding, H and D are also corresponding angles, and they're equal to each other. Alternate angles, D is equal to F across the transversal here. Angle D is equal to angle F, just as angle C is equal to angle E. All right, alternate angles. Okay, next one is co-interior angles. So C plus F will sum to 180, just as D plus E will sum to 180. All right, let's have a look at a parallelogram. For a parallelogram, opposite sides and angles are equal. So you can see that the line AB is parallel to the line DC, but it's also equal in length. And just as line DA and BC are parallel and equal, angle A and C are equal, angle D and B are equal, and the symbol for showing that the line AB, that's this bit here, with the little line above it, that's line AB is equal to line DC. That's the length of the line AB is equal to the length of the line DC. Length of the line AD is equal to the length of the line BC. Okay, let's go a bit further again. Isosceles triangle. Isosceles triangle. Here you have these two sides here are equal in length. Angles A and B are equal, and then if X is the midpoint, then the line AX is perpendicular, and that's the symbol for perpendicular there, is perpendicular to the line BC. I'll look at some circle geometry. Now, the angle subtended by an arc at the center of a circle is twice the angle subtended by the same arc. So an arc is a curved part of the circle. Okay, so we're looking at the arc from A to B. Okay, so the angle subtended by an arc at the center of a circle, now here's the center of our circle right in here, okay, is twice the angle subtended by the same arc at the circumference. So in other words, this angle here, the X angle, is double the Y angle. Okay, that's what we're trying to get at there. All right, Next thing, it's the angle in a semicircle is a right angle. So if you've got a semicircle, it's half a circle, so you have the diameter here passing through, and there's our center of our circle. Then the angle in a semicircle, that's this one here, must be a right angle. Okay, angles in the same segment of a circle. And to give you an idea of a segment here, just think of the dotted line, and all that region in here is a segment. So just over here, if you look, this bit here, here's the shaded part, is the segment of our circle. Okay, and the angles that the angles of a circle are equal, that all lie in the same segment. So you've got angle X, Y, and Z are all equal, because for that simple reason, they all stand on that same line in the same segment. Okay, some others. Okay, again, if we look at the angles, this quadrilateral inscribed inside the circle, inside a segment of the circle. Okay, if we notice here that they add up to B plus D will add to 180, A and C will add to 180, and angle B will be equal to angle E. Some of these, we're not going into detail as to why, but you could establish arguments for those. I'm just going through some basic properties, some geometry. All right, so here we have a circle. The center is at O, and we have two tangents. Okay, we know they're tangents because they touch the circle here at this one point, and they're perpendicular to the radii. Okay, now these two tangents extended from the points A and B meet at the point X, and one thing we can draw from this, if you look at it quite, you're going to have a case here of similar triangles here, because you've got XA is equal to XB, so the line XA is equal to the line XB in length, and the line XA is perpendicular to the line AO. And also, as a result, you can see the two radii are equal. You can see the two right angles here, and you'd expect then that this triangle here, triangle XOA, okay, will be identical to triangle XBO. Okay, and almost here. Another thing, another property here is that the angle between a tangent to a circle, so here's the tangent, the long line at the bottom here, and a chord through the point of contact, so there's your chord here through the point of contact, is equal to the angle in the alternate segment. Okay, so the angle in the alternate segment, so that angle A is equal to angle B. Okay, so you can see a chord here. Okay, so the angle between the tangent to the circle, this one, and a chord through the point of contact, okay, is equal to the angle in the, so that's angle A, and that's now equal to the angle in the alternate segment. Okay, so here's the alternate segment. Okay, that's angle B. So angle A is equal to angle B. And that is it.